Okay, yeah. Welcome to my talk, Simplify and Secure Equation Systems with Type-Driven Development. And let me begin with a story. So this is Leah. Leah is a mathematician working in the field of optimization and optimal control. And today, Leah is on board the research vessel DNAP in the harbor of Rostock in Germany. Her goal, or better, the goal of her software is to autonomously steer the ship towards the pier and stop at a predefined position. Leah is quite nervous because the test is important to the project. The project is almost at the end, and testing time on board the ship is quite limited, so it's really important to get it right. But she is well prepared and hopes for the best. And in fact, the first test run is almost perfect. The ship stops where it should and goes a good trajectory. But the crew tells her, yeah, the rudder was turned a bit too much, and we do not really do that when we are driving, so can you maybe change something? And she thinks and says, yeah, there's actually a small thing I can tweak, and that will solve the problem. And she does that. However, on the next test run, nothing works. So the trajectories are quite wiggly. The ship doesn't stop, the speed doesn't go down, and so they cancel the test run. Afterwards, she looks at her code and directly sees the mistakes. It was a small index mistake. When she put in a new constraint, she forgot to update one of them. And so Leah is quite, thinks it's a big fault. She thinks she wasted time of herself, of her colleagues, and of the project. But her colleagues tell her that it's okay. Mistakes happen all the time, and especially these kind of index mistake in this code happen all the time. But Leah is of a different kind. She doesn't take that happens all the time as an excuse. She sees it as a chance to change something and to look deeper into it, maybe to solve the problem. And that's where my talk today is rooted in, to make a case study of if we can change this with modern C++ or with C++ at all, to make one kind of bug just go away. Oh, yep, there was one more information. But before we start, some words about me, about the author. So, hi, I'm Arne. I worked as a research assistant in optimal control of ships, cars, and electrical grids, which are, from the point of mass, quite the same, and so are the mistakes we do. So the equations behind them are all the same, and we do these kind of index mistakes all the time, and that was where I thought, maybe we can change something about that. Next, who is Leah? Leah is a persona I invented as a user of my code. So someone who cares about correctness, about clean code, who uses the library I'm writing to solve the problems in her day-to-day work. She has 2 years of experience, so she starts to see where problems are recurring again and again, and she asks me questions or does suggestions about what I can do, what we can do with the code. A small warning, Leah and I are both mathematicians, so I have some slides with math equations on them. But don't worry if you do not care about math. All of them are written in code on the next slide or even on the same slide, and just skip the slides if you do not want to understand them. But they are important for the motivation of the problem behind all this. And with that said, let's start with a simple equation here. So equation system, I'm talking about the equation system from the topic. So that's the motivation. These equations actually describe in a very, very simple form the movement of a ship. So it's a derivative equation system. So if you remember, derivatives describe how things change, and here how they change over time. And it says that the position changes based on the velocity and your direction you're looking in. The direction also changes based on your rate of turn, and the velocity and rate of turn change based on your propellers on the ship. So very simple thing. There are a lot of effects not considered here, but these are the kind of equations we have. If you look at the code, which is typically used to describe these within the working group, it looks like this. So you have input array, you have two input arrays, one output array, a lot of hard-coded indices, a lot of hard-coded things here. And you might know, okay, this is predestined to have some bugs in it. When you change something, you will always, at some point, forget to change the indices. Maybe if you are in your office and have a lot of time at the beginning of the project, you might be able to do it correctly. But if you are on board of a ship and are seasick and have the pressure of the next test run is coming, you will not write a unit test for that. You will just change it and hope that you are doing it. And figuring out the bug when you are seasick is one of the worst experiences I had. Yeah, so let's look at what we are doing here. Maybe first, let's one remark here. Here is even a bug on the slide. When I prepared the talk, I swapped the equations, the order of equations, and I forgot to update the index. But a bit more of context where this code is in the ecosystem of solving things. So you will find these kind of graphics throughout my talk. On the left side, you have in red the output array where we are writing things to. On the right side, you have a big input array where we are always considering a chunk from, so the blue things. And in the middle, you have the equations which are referencing the input array. So they have an index and say, okay, the position or the velocity corresponds to index so-and-so within the input array. You might see that the input array is larger than the output array. That is because we have two types of things which are important to maybe understand the words I'm using today. So we have the states, or so-called states, that are the things that change over time. So like the velocity that changes within our ship. And we have controls that are things that we use to change these things like our propeller speed or something like that. So you will hear me talk about states and controls. These are states and controls are in the input, and only the states are in the output, just to get the words right. And then, of course, there's the surrounding thing when we are solving these things. So we are writing to an output array that gets to a solver which computes new input for us, and then we are getting a new input array. So just to give you an overview where this code is rooted at. But the user can only influence the blue and red things in the, at the bottom. And it is a high-frequent loop here, so performance is not unimportant, but most of the time goes into the solver itself, so it's also not the thing where 1% more performance really matters. Okay, so let's begin to solve the problem. What are our goals today? So the main goal is prevent bugs through compiler checks. So we really want, if the equation system is not correct, it should not compile. Or even that the compiler helps us that we cannot make the mistakes anymore, so it does something automatically for us. The next thing is that it is intuitively usable by mathematicians. So someone like Leah, someone who is 2 years into programming, has a master's degree in math, not in software engineering, or in, not in software, and really cares about the equations and not so much about the implementation details behind that. And does not have so much experience in software engineering. So if you tell them, yeah, you have to take care to not hard code your indices, you will get bugs by that. It's maybe they are not so much interested in that, and they care about algorithms and so on. So it needs to offer to these people something that they care about, and that are the words like velocity, position, a ship, things like that. And the last thing is that it should be maintainable. So you will see a lot of templates, a lot of template parameter packs, a lot of variety templates and so on. And you might know that if you go too deep into this world, it might solve the problem, but no one understands it. And then your library will lose usefulness after some time. So not too much of a magic behind that. Okay, next equation here. Let's start simple. This is a very, very simple thing. It says, okay, I have a position in x, which changes with my velocity. So the velocity influences this, and my velocity changes based on a propeller on my left side and a propeller on my right side. And that's, as a tree, you see, okay, I have the input array on the right side, The position, velocity, left propeller, and right propeller are the domain words which are references to this input array. Then I add the propellers together and write them to the output array in red on the left side, which are the derivative values of the position and the velocity. So basically, when you look only at the code, you have an input array, you want to reference the input, add things together, and write it to an output in a specified thing without the chance of confusing the indices in it. Let's start. Okay, first thing is, how do we get values from the input array without hard coding indices here? So wrapping a meaningful word around an index and makes the compiler be able to distinguish a position from a velocity, so that the compiler knows, okay, a position is something different than the velocity. And for me, that sounded somehow like a strong type. So a strong type is a wrapper around, for example, a double, to tell the compiler, yeah, this double is something different than this double. So, but here we are talking about indices, so really about the value of the integer. But still, so let's make some types. We are type-driven in this talk. I decided, yeah, make a simple quantity type with a tag so that you can give it tags and define new types and tell the compiler, yeah, position is something different than the velocity. Now the compiler knows, okay, there are these words, they make sense for me. But how do we match them to indices? How do we define, okay, this means some index in some system? So I needed a list of types. I thought a list of types is probably a tuple. Even if I don't care really about the value within the tuple, I only care about the type part here. But still, so now I could say implicitly position now has the index 0 within this tuple. And the compiler also knows that it's there. The problem there is that it's easy to get the value of a tuple from an index. It's also easy to get the value of a tuple from a type. But there is no direct way to get the value or the index within a tuple from a type. So these two functions at the top are not matched together. And that's where my first library code comes in. I created a class called index, which gets a type T and a tuple, and then computes the index. And the trick is here. Of course, I just Googled the trick. You find from whom. And the trick is to create, at compile time, an array with the same size as the tuple, and then initialize the Boolean values within it based on whether they are the same type as you are looking for. So hopefully you get an array with only false values and one true value in it. And then, yeah, by folding over it. And then you can use the STL algorithms to find it, and if you find it, return the index by computing the distance, and if not, throw an exception, which will lead to a compile error when you are at compile time. So now we have a way to see, okay, I want to have this type, what's the index in the tuple? And we can define a convenience function around that so that's easier to access. And then we see, okay, if you have a tuple of int double float, we can now compute at what index the double is. The next question is, okay, now we have indices. We need to get values from an input array based on these indices. And I decided to go and give the quantity, so our strong type itself, the ability to get its own value from an input array with this evaluate function that gets the list of quantities, so one template parameter here, and an input span or an input array here, and returns the value within the array of itself based on the list of quantities. If it's not in the list, it will not compile. It will throw an exception at the compile time. And so, yeah, if it's there, it will return you the value. And with that, our user can now write new code Leah can now define a position, define a velocity, and ship state here, and then call velocity evaluate for an input array and gets the value back without any index involved at all. However, as Leah mentions, okay, now we replaced x0 with a quite long expression here. And in fact, one of the first versions of my library made the user do something like that. I presented it even to my team, and they told, yeah, it's interesting, it solves the problem, but we will not use it because it's ugly or too complicated to write. And that's, yes, that's true. If you really write an equation system with these kind of expressions, it explodes in your code, and you will not understand it. So we need to dig a bit deeper here. But yeah, we still have time for that. So let's look in our tree at the next position. We want to add two things together. So now we got the values from the input array and need to add them together based on the domain word. So we don't want to say add index 2 to 3. We want to say add the right propeller to the left propeller value. And for that, I created a new type called add here, which has the same evaluate function, so the same signature as the quantity. And it gets two types, any type so far. And when evaluate is called, it evaluates the left-hand side, then evaluates the right-hand side, and adds them together. Simple as that. And it takes any type. And it has the same signature as the quantity, so it's composable. You can also add other operators or add two additions together. And then for convenience, you can define an operator plus, which gives the thing back. However, small thing maybe to note here, a small step aside. Okay, now we have an operator plus for everything, because it takes any type so far. But we are able to use C++20, so maybe we can constrain it with a concept. And let's do that to just see how it's possible. So let's define a concept, system expression, which is quite important because it defines this evaluate signature, which is a very fundamental thing within the library. And just says, okay, I want to have an evaluate function that you can evaluate on an array and a list of quantities. The problem is that it has template parameters itself. So you cannot directly invoke them because these parameters are part of the evaluate function and not part of the type. So the compiler does not know them at the point where operator plus would be called. That made me think quite a lot of time, even if the solution might be easy to that. But it was really something to wrap my head around because, yeah, it's a thing of the type, but it's not really within the code, not a trait of the type. But maybe we can define a subsystem of our overall system where we say, okay, this is a minimal system our type needs to work on. And if we look back at our tree here, at the position where the plus is, we see that the compiler knows everything to the right here. So everything in the yellow box is known to the compiler at the time where we instantiate the plus operator. And so we can define a subsystem on which the evaluate function must work. So because it must work on a system of two quantities, a left propeller and a right propeller, and then at least an array with two input values. And the idea is to propagate this information to make it accessible at that point. So we define, okay, it depends on. For a quantity, it depends only on itself, a tuple of itself, so type list. And an addition also depends on everything the left-hand side depends on and everything the right-hand side. And then we can concatenate that and use the unique tuple type, which just eliminates duplicates in that list. And with that, we now can define our subsystem, say, okay, we need an evaluate function for at least the dependencies of my operator or of everything within my operator and for the size of these dependencies. I'm looking at it here because this depends on becomes important later, so try to save it in your mind, but I will get to that later. So back on track now. Let's see, with our new ability to write operators, what the user can do here. The user can now define quantities, ship states as a list of things, and equations. So a dot position is equal to velocity. A dot velocity, so derivative of the velocity, is equal to the sum of the left propeller and the right propeller. Okay, we have still this quite long evaluate thing at the bottom. But if you look only here at the top, you might see that something nice tries to emerge here, so that where you do not have any indices at all, and which really looks like the equation system we had before. So maybe let's move forward and look where we are going. Our next task would be to get the value of an expression, so the sum of things, to the output array. And the output array describes the derivative of something. So it's the derivative of a position. It's not the position itself. But important is if position is at index 0, the derivative also needs to be at index 0. That's an invariant of the solver that needs to connect these types. So we need a way of connecting the operand, so the position, to the expression of its derivative. Might be some math terms, but we just need to connect the expression, so adding things together to an output index. For that, I created another class derivative, which has an operand, so the thing it's working on, the position or velocity, and an expression, so the thing that describes how it's evaluated, so the thing on the right-hand side of the equals sign. And then defines also an evaluate function, which just delegates to the expression here. So it really connects the operand to the expression. And then we also have a small convenience function, or it's at this point really needed because the expression is deduced by the compiler, because it can get quite long, but the operand needs to explicitly state it by the user. So the user says, okay, the derivative of the position is this long term or something like that. And with this function called dot, because it's demarked as a dot in math, the user can now go back to the code and write it like this. So if you look at the equations in the middle, the dot position, which had the information that it's working on a position only in the variable name so far, now has it really in the type. So it really connects in the type of the thing, the position to the expression, which is here just the velocity, or even the derivative of the velocity, which is the sum of both propellers. So it's now not something you have in a comment or in a variable name or somewhere else. It's really in the type. The compiler knows about this connection here. And it starts even to look like LaTeX code, which is quite good for mathematicians here. If you look at the bottom, you can now see, okay, we are getting the index of our operand, of our position, writing in an output array the value of the evaluation of our derivative, of our dot position here. Of course, you can still confuse those. There's no way to connect, or here is no way to connect the left-hand side of the equal sign to the right-hand side. But we can change it so that it's not explicitly stating the position operand, but it's computing the operand. It uses this member of our derivative to compute the output index, which might look quite complicated here, and you can still confuse it. But what you might now see is that the compiler can do this for us, and maybe we just need to give the compiler a list of derivatives and then let it do its thing, do this complicated thing itself. So maybe we want to move from the user defining the equations here but moving towards the user putting them in a list themselves. So we are back to, okay, we have a lot of types. We want to have a list of these types. So the user might just do this, define a custom type, ship motion. So the name there is not important. But the type needs to have a make dot function because it makes our dots here, which returns a tuple of the derivatives. So here we use the values, the variable dot position, but it's really important that the tuple now has all the information it needs within the type of the tuple. So you know, okay, the derivative of the position, that's the type, and it has this expression, which is a member of the derivative. And with this list, we can now define our cornerstone in the library, which computes everything we need from it. And that is this class. It's a bit more complicated, so let's go step by step through it. It's a class that gets 3 parameters, 3 types, a list of states, a list of controls, so what I was talking about at the beginning, and a derivative system. That's the class that has this make dot function. So we have 2 tuples with types and the derivative system. Then the class computes the size of everything, so the size of our states and the size of our controls, and defines an evaluate function that gets an input array of the combined size and an output array of only the size of the states. And then it calls the make dot function on our derivative system and iterates over this tuple, a tuple for each, which applies a templated function to each type of this tuple, or even each value, but we care about the types. And this templated function here computes the complicated thing from the 2 slides before, the output array based on the operand of the derivative. That's the first line. And then writes to the output array the evaluation of our derivative. So now it's every information is within the types, and we can really define a class that automatically does everything. Yes, you could still confuse them, but there's only one class, so you have to do it once correct and not over and over. So it's really this one thing. And our user's code would now look like this. Still the definitions at the top. The derivative system, so the ship motion here, which gives us the list of our derivatives. And then at the bottom, you see, okay, the state space system, which is a name in mass for controlling these things, which gets the states, the controls, and the ship motion. And then you can call evaluate on it and compute everything without any index involved and without any way to confuse it. You can swap the equations as you want at the top. The compiler will take care of the indices behind the scenes for you. Yes, there's still an evaluate construct, but now it defines the whole computation of the whole system. So it's really, not that bad. It's one long line, but yeah, I think that should be okay. So now we eliminated our first problem we identified through the types. We gave the compiler all the information it needs to compute all the indices for us, and all the user needs to do is now really write things that look good in the domain of the user, so that uses words that make sense in the domain of a ship. But we still have time, so there are more problems to solve here. The next problem is, in an equation system, there might be things that are not correct, but not coupled to indices. Things like this. If you see, okay, I have A over B plus C, you can write A over B and then add C. I have personally done this mistake quite often. Most of the time spotted it directly, but it's still there. And it has nothing to do with indices. So our goal that if it compiles, it's probably correct, would not hold if you allow the user to do something like this. Of course, this is a known problem, and it's, let's call it solved so far, because you can check it with units. So because if you apply units to these values and say, okay, A is meters and B and C are seconds, you can see, okay, I can divide meters by seconds, but I cannot add seconds to meter per second. That's just physically not allowed, or does not make sense. And there are frameworks out there which already dealing with this thing. So my idea was not to rewrite such a framework, but use one of them, and I used the units library from Mateusz Pusch, an older version. So there's version 2.3 or so out there already. I still using the older version because, yeah, it's on my to-do list to update that here. There was not enough time. But how do we bring the units to our quantities here? First idea is, yeah, just give the quantity a unit. So the user can say, yeah, this position is in meters. Small comment on that. If you're dealing with ships, you do not only have meters and miles, you of course have also nautical miles, which are not the same as a mile. So one more way to confuse everything, which is quite good. So it's really important here to say, okay, we are dealing with meters. Yeah, so now our quantity has a unit, but what can we do with that to check if an expression is correct? Let's look at our operator. In addition, how that can use the units library, and we can say, okay, we expect the left-hand side of the operator to have the same unit as the right-hand side. I know that the unit library can do much more than that, and I want to include that too when I move to version 2, but this is somehow a proof of concept that I can use units to check things. So because you can also add a meter to a kilometer, for example. That still makes sense, but wouldn't satisfy the requirement here. But then our addition can have one of the units, it just picks. The unit of a derivative is somehow a bit more complicated because it needs the unit of the expression. Okay, we have that, but it's not the same as that of the operand. It's the division by time because it's the derivative in time of that operand. So we need to compute that in our type, but yeah, with some decal type, and so we can do that, and then define a concept which checks if the expression is really a derivative in time. And with that, we propagate the units through our framework and can really check if everything fits together. And that might seem like a simple change. When I introduced it into my library, it made writing unit tests, for example, way harder because I was always, I'll just add things together. And now I really had to think about, can I add these two things? Which units do they need? What if I have a multiplication? So it makes it really hard to write incorrect code if you have units in your system. So that's really a good thing. Back to the code of our user. All they have to do is specify the correct units in the quantities. The equation system itself does not have to change because it does everything behind the scenes. But now you can really couple the units to your quantities here, which is also very good documentation. If you look at it, you do not have a comment, maybe outdated, if it's in meter or something else. You really have a type which is telling this to you, and your compiler can check that. Okay, so we eliminated a lot more mistakes here, and I can really say it's quite hard to write incorrect code with the units applied. So let's check what we have achieved so far. This was the code we were beginning with. A lot of indices, a lot of implementation detail, let's say. Less words that make sense to the user. And this is the code now. I would say it's quite beautiful because you do not see any index, you do not see any array here. You only see the equations the user might specify here. So our more complex system from the beginning. You see the things I was telling you at the beginning, yeah, this means velocity, this means yaw things. You really see that in code. And the compiler can check if what you have written makes sense, if you maybe confuse the multiplication with the division or something like that. It will not compile if it does not make sense, or even the indices are computed for you. So that is really good. However, it's not the whole truth because this is our user's code in reality. So quite a lot of definitions here. It's longer. I don't think that makes it worse because shorter code is not always a better code. Maybe it just hides complexity. But nevertheless, it might be quite tiresome to always rewrite these things for the user, especially if you want to prototype fast. And so let's just see if we can do even more with C++ here. The first thing I want to look at are these 3 lines at the bottom that are our definition of states, our definition of controls, and our, the whole state space system. If you remember what I told you at the beginning is what are states, what are controls. So the states are the things we operate on, the things that change over time. So the operands of our derivatives. So everything we have within a bracket of the dots that are the same types as in the states here. And controls is every quantity on the right-hand side that's not in the states. So our derivative system, our type here already defines it implicitly. We just need to make it accessible for the user. And that we can do with some more templates. Short recap of our class derivative, because that's where the words are now coming from I'm using in the next few slides within templates, so it might be good to remember them. What's important is here. So a derivative couples an expression, which is the equation it's describing, with an operand, so our position, velocity, so that's what a state is also. And it has these dependencies we used in our concept earlier. So it knows what it's depending on. All the quantities that are within the expression, it knows here that, I'm depending on these things. And those informations we will now use. First, automatically compute all states defined by a derivative system. So a derivative system is a list, a tuple of derivative equations here. And getting all states from that is quite easy. You just get the tuple, do a fold expression over that, and get all the operands of the equations and define a new tuple with that. And then you have all states. So it's basically a simple transform. It's a type transform, if you want to say. And then you can define the system states at the bottom, and for utility, and say, okay, get me all the states defined by the system, and then it calls the make dot and transforms them to the operands. Computing the controls needs 2 steps. First, we need to know all dependencies of our whole system, not only of one derivative, but it's the same way. We are transforming a tuple of derivatives, getting to the depends on member, making a new tuple of that, or because that are tuples, we concatenate them, and then use this unique tuple again to remove the duplicates in it, and then return that. And with that, we can then compute our controls by first computing all the states, then computing all the dependencies from the 2 slides before, and then forming the distinction of. So this distinct tuple of basically gives us everything in dependencies that is not in states. So a set distinction of those both things here. And then, again, a type trait at the bottom to make it easier to access it, which calls the make dot and gets all the controls. And then we can define a simple redefinition of it. Say, okay, we have a state space system of which only needs 1 parameter, and compute the other both from the equations or from the slides we just had. And that removes our user code or reduces it. Two lines saved. But a lot of redundancy here removed, and also it shows a way of how much information we already have within our types here. And we are not done yet. We still have some time, so let's look at the next thing. Here at the top, you see, okay, we have all these quantities, all these position, velocity things the user needs to define. And you might notice that some of them are quite generic. So a position is not really a ship thing. You can apply it to many things. You can apply it to cars, to spaceships, to all kinds of ships even. So maybe you can just say, let's do a library out of them. And the code doesn't require you to use it only once for only one system. So it might be that within your team you say, okay, let's just have a header that defines all the quantities for us. Same as you use a header to define strong types for you and then reuse it. So for now, let's consider those also to be some library, even not mine, but some domain library, and not user's code here. So then our user code is only this. And that's already, once again, only the lines that describe the system. So it's already quite simple. But we can do even more. So we have seen the power of what we can compute here based on templates. So maybe we can do more and enable the user even more to make cool things, to reuse the code they write. And talking about generic things, the first 3 lines describe, I mentioned it at the beginning, you move or your position changes based on your velocity and the direction you're looking in. And then the direction you're looking in changes with your rate of turn. And that's also a thing that's not only applicable to ships, that's applicable to me, to cars, to spaceships once again. So it's quite generic. And it would be cool if the user can just use a combination of these things and say, okay, we have this generic part, I can reuse that for all my applications, and I just want to write the specific part for each ship. So something like this, where you have the generic equations here at the top. So it's the motion in 2 dimensions, and then the specific equations here at the bottom. I call it a turnable propeller because that's what we have at this ship. These equations describe how you steer a ship based on propellers that can turn themselves, so they can push you forward and turn the ship. That's quite common nowadays in ships to do. And then the user just has to do a combine of both. For this case, it would be easy because you can just concatenate once again the tuples because they work on different things. The top system works on different states than the bottom thing. But there are more complicated systems. And I wanted to look into the complicated things because, this one does not really need special treatment. More complicated thing can be seen in ships too because, we have the turnable propeller. You might think, okay, a ship has a static propeller, so a big propeller at the back that just pushes the ship forward. And yes, that's still a thing. And ships tend to have this combination of actuators. So it's even like every ship needs to have a different combination, not 2 can be the same. So for example, the turnable propeller, I talked about, and the static propeller. And the difference is that the static propeller only influences the velocity. So both systems influence the velocity, but only one of them influences the rate of turn because only one propeller can also be used to steer the ship. The other one not. You would need a rudder for that or something like that. And ships combine these actuators in very different things. So it would be good or would be quite cool if you have a library of propellers and then say, okay, my ship combines them and the code does the rest for me. So let's do that for our user. So let's see what we need to do here. As I said, these influences. So let's see what we need to do first. We need to get a list of all the operands, all the states, all our combined systems have together. So velocity and rate of turn, merge them together here. Then for each operand, we need to find the expression in each system, if they have any, and combine them to a new derivative. So make a new dot based on that and add them together. And if you have only one of them, just use the one. So use the things you have, but do that for each state. Okay, let's do this to-do list within code. First, we compute all operands. That's more easy to do, or easier than the rest, because we can reuse our states computation from before, and now fold it over all systems. So we get as a we get a parameter pack of the systems we are providing, and then fold it over, get the states, put them together. They are tuples once again, so we concatenate them and eliminate the duplicates. That's a pattern you will see a lot here. Okay, but how do we find these expressions? So what we need to do is, for one operand, so say for velocity, we need to find out if a given list of derivatives defines a derivative for this operand, because it might be that some of them are not influenced, and then do something based on whether we have it or not. So for one operand and one system, we can say, okay, if we look into the system look into all operands of the system, and it contains the one we are looking for, then we return the thing at the bottom, which is basically return a tuple with only the expression for this operand. So it says contains here, it looks into the tuple, and then it returns a one element tuple consisting of the expression we are looking for. And if it's not present, we return an empty tuple, because we need to return something. Why are we dealing here with tuples again? That becomes clearer if we look at how to combine them. Because in order to combine now all expressions from all systems we have in our combination, we do this. We fold over all the systems for one operand. So we go over our turnable propeller and our static propeller for the velocity, and look if they define something for it, put that all together, and concatenate over it. And then there's this cool thing that if you concat tuples with empty tuples, the empty ones go away, and the other ones will form one big tuple, which you can then use to combine and then fold over them and form the sum of all of that. So that's quite a cool feature here for C++, I think, especially that, if you have only one element in it, it still works with the fold expression, even if there's no plus occurring afterwards. So that's for one operand and all systems. Now, the last step would be, okay, forming a new system based on all systems and all operands, and that's now where you can really say, okay, maybe maintainability becomes an issue because we have two parameter packs, two combined fold expressions, but it's really at the end here. What we are doing is folding over all operands, over all systems, and then defining our new systems. Might be a bit complicated if you do not directly get what that does. It's okay, just remember that we can do our combination with that. It was quite hard to find the right spot for the ... dots when I was programming it, even if it's only one line of code. It's hard to write sometimes. And then at the end, we can form our combine type here, which computes all the combined operands, like in the first slide from this, and then define a new make dot function which does this combination over all systems and over the combined operands. So I might have lost you at some point with all the fold expressions. That's okay. Just now get back on track here, so we have our combination. So we can go over all systems, over all operands at compile time and combine them together with, for our user. And then when we look at the user code, now we have the motion 2D and the turnable propeller from before, and the user code just says combine. That's the cool thing here, that the user does not see any fold expression at all. So the hard things are hidden in the library where people with a bit more experience can look at them, and the user just see, okay, I can give any number of template arguments. Maybe they don't even know that that's a cool thing of C++, that they just say, yeah, it's possible. And if you say, okay, but the ship has more propellers, and for the next use case we want to consider the other one, then you can just say combine, and the compiler will resolve any index for you, will do that, just based on the types. Maybe to mention here, everything is based on the types. Sometimes I was using the values because it makes it easier in the code, but there is not really much instantiated here. It's all gone through the compile time things. Yeah, with that, we are going towards the end of the talk. Let's look at how far or what we have achieved for our goals. I'm not asking if we are done. I learned yesterday that's a complicated question. But what have we achieved for our goals? So the first goal was prevent bugs through compiler checks. The most important bug was the index bug. That's not even prevented through the compiler checks. The compiler does it for us, so we cannot even make the bug anymore and make a system that does not compile. It really just does everything the work for us. It checks with units if our expressions make physically sense, which is then always a good way to check if we have typed it incorrectly from the paper we were looking for. The next thing is intuitively usable by mathematicians. So if you remember the user code, yes, there's only domain words in there. So there's no more array in it, no more solver implementation detail for the user. They only care about, okay, how I describe the ship movement and how I combine my system, and everything else is done by cool C++ features for them. It's even so much in the background now, this implementation detail, that you can do other things with the code. So I implemented, for example, a format function for the system, which gives me the LaTeX code for my system so that I can use it when I write papers about it, which eliminated one more bug, that I make a typo when I write papers about it. So that's also a cool thing. So we can really abstract it away, the implementation detail. The last question was maintainable. So yeah, it requires some knowledge and some getting used to parameter packs. So the last slides I might have lost some of you because they are hard to understand directly, because they do not really show what the code will look like for the compiler. And doing them is even more harder. It's not that much code. All of the library has a few hundred lines of code, maybe less. But getting the ... at the right position is sometimes hard. But I think we can say that the maintainer of the library has more experience than the user. And that's a cool thing. You have in your team, in the working group, you might have one or two people who are interested in these kinds of things, and the others are interested in the domain. And so these one or two persons can really provide a cool library for the others to help them with their things and get this knowledge, and the user does not need it. Yeah, and so with that, I'm almost at the end. So if you want to look at the code, here's a Godbolt link where you can directly play with it. I will publish the slides later, so you can get that. Or if you want the whole code and want to use it somewhere, it's also in a GitHub repo to play with it. And with that, I'm done, and thank you for your attention. Okay, questions? Yeah, do we have a microphone?
Thanks a lot. Thanks for your talk. I really like the fact that you used a units library to make sure that the operators like plus, minus, and sinus are working on the correct units. It seems like you're not doing it for the assignment. Like when you're moving outputs to inputs, there might be potential for confusion there where you assign something to an incorrect unit. Maybe I got it wrong. Can you talk a little bit about that?
Yeah, maybe. So the derivative checks if the unit of the operands it's working on fits to the expression. So this was this time derivative of value. So that's where you assign it. So it is checked at that position. Yeah, maybe a bit more about the units, because that's really just a basic implementation. I really want to use the features of the units library, not only check if it's same as, and I'm wondering if my evaluate function can be templated on the return type and directly use the units, and then it will does everything for me because it checks everything. And you can also use this kind of relationships and so on. And so, yeah. More questions? Yeah.
Yeah, thank you. So I also like the fact that you basically decouple the tag types, which are like the strong types, from the actual array that is just plain old doubles. But it seems like the indexes are also potentially maybe decoupled. Like, if I understand correctly, the order of inputs inside the array is exactly the order of objects in your tuple.
Yes.
And that's why you implemented the get IDX function. I wonder if maybe perhaps it, like whoever chooses the order is sometimes like a hardware vendor or someone else. Maybe it can also be decoupled, and regardless of the ordering of the types in the tuple.
Yeah, so you're thinking about that we check if a reorder of the things would make it like more cache friendly or something. Yes, that might be a thing. I just did not have this situation where the order really mattered for performance or something like that. But yes, you could do that by, so now the user can somehow influence the order, but yeah, yes, probably in the future you can find a way.
Thank you again. Since you're using a lot of parameter prac and compile time expressions, what are the implications on compile times? Was it a concern for you, or?
Yeah, that. So question about the compile time, that's a question I always ask myself because they can get quite high. I did not measure them, how they impact the compile time of the overall system. The good thing is that the usage of this library will be probably within one CPP file and then not leak outside of that. And so you have to, don't recompile everything if you recompile that. And when you're considering the applications on the university here, compile times are not that large because it's project code, smaller things, not grown over such a long time. So compile times are more in the minutes direction. So far I did not see that, but yeah, that will probably be an issue if you really go farther out, and then you will experience it. I plan to measure it, even maybe profile it for some applications, and then see what we might do there. But yeah. Okay, some more questions? Okay, if not, then yeah, thank you all for your attention and have a nice day.